Let's talk about basis and dimension for vector spaces. So here's a definition. Let V be a vector space. We say that some set of k vectors spans our vector space if everything in my vector space, so every little v, can be written as what we call a linear combination of these k vectors. And what I mean by a linear combination is I'm going to take some scalar times the first one plus another scalar times the second one, all the way up to some kth scalar times the kth vector in my spanning set. And the point is, every little v is supposed to be written for some scalars, C1 through Ck, in this form. So if every little v can be written in this form, then we say that this set of vectors, v1 through vk, spans my vector space, capital V. And here's another definition. If we have a set of k vectors that is both linearly independent and it spans V, we say that it's a basis for V, that this set of vectors is a basis for V. Here is a fact that I will not prove. So it's possible and likely for most examples I can think of for vector spaces, it's possible that it has multiple different bases. Right. Bases is the plural of basis here. However, every basis is going to have the same number of things in it. So if I have a basis that has k vectors and you give me a different basis, the vectors might be different, but there's still going to be the same number k of them. That number, meaning the number of vectors in a basis, is called the dimension of my vector space, capital V. And I denote that dim of V. Yeah. I should mention it is possible to have an infinite dimensional vector space, like the vector space that we've talked about that consists of all functions from R to R. That's infinite dimensional. Most other vector spaces that we're going to talk about have finite dimension. And of course, dimension is a word that this is not the first time you're hearing that word, and I'm sure you have some intuitive notion of what the word dimension means. If I were to ask you what's the dimension of R3, you'd probably say 3. This used to say n, but then of course with an n there, it's still true. The dimension of R to the n equals n. But then I decided let's just make n 3 just for concreteness here. So, like I said, I'm sure this corresponds to your previous use of the word dimension. Anybody would call this three-dimensional space, R3. That's what we call it. But now that I'm using the word dimension this other way, let's check that everything checks out. So why, according to the definition that I just gave, why is this a three-dimensional space? So what I'm going to do is I'm going to give you a basis that has 3 vectors in it. This is your probably the most standard basis of R3. It's basically just the columns of the identity matrix. Oops, why does it do that? Right, so it's just, ones down the diagonal and zeros everywhere else. That's our basis. So why is this a basis? Let's see here. In order to be considered a basis, this is just the first page. Remember that it needs 2 things. It needs to be linearly independent, and it needs to span V. So let's check those. So why is it linearly independent? Well, one way we have the shortcut we learned last time to check whether three vectors in R3 are linearly independent is to just do the determinant of the matrix that I get by sticking these three things in a matrix. And like I was indicating before, that's just the identity matrix. And we went over this. The identity matrix, the determinant is 1. We could do this multiple ways. Maybe the quickest way for me to explain is this is upper triangular, or if you like, it's also lower triangular, and the determinant is just the product of the diagonal entries. The determinant of the identity matrix is 1, not 0. So, right, if the determinant is not 0, then the vectors that you made the columns out of are linearly independent. Okay. Why do they span my vector space? Well, in order to check that, I'm supposed to take an arbitrary member of my vector space. So I'm going to take any vector that has 3 coordinates, let's say x1, x2, x3, it could be anything. I would like to find, going back to this definition, I would like to find C1 through C3, because K is 3 here, such that my arbitrary vector is equal to C1 times my first basis element, plus C2 times my second basis element, and then C3 times my third basis element. In other words, here's my arbitrary vector. That should equal C1 times my first basis element, C2 times my second basis element, C3 times my third basis element. As long as I can find C1, C2, C3, possibly and likely depending on x1, x2, x3, to satisfy this equation, no matter what x1, x2, x3 are, that's checking that these span my vector space. And this is going to be easy. If I add this up, this is just C1 times 1 and then 0 on top. If I go across the middle, I've got 0, C2, 0. If I go across the bottom, I've got 0, 0, C3. So my solution is C1 is x1, C2 is just x2, C3 is x3. So sure enough, they do depend on x1, x2, x3, and that's fine. The point is I'm always able to find a C1, a C2, a C3, no matter what the x's are. So there's a basis with 3 vectors in it, and that proves that the dimension is 3. Of course, like I said, this is your sort of like classic, absolutely standard basis. There are plenty of other different things I could have said. Just to throw something out there. Maybe I'll have the same first one, and then maybe I'll have 2 1s, and then maybe I'll have 3 1s. And I'm not checking any of this, but I promise you this is also a basis. In fact, if you pick any 3 random vectors, as long as they're quote-unquote random enough, and I'm not being very precise with this statement, with probability nearly 100%, you're going to pick a basis. It's kind of it's a pretty big coincidence if you manage to pick 3 vectors at random that aren't a basis for R3. Anyway, let's do a basis for something else. So we discussed this last time, that if you have a homogeneous system of linear equations, homogeneous meaning that the right-hand side is 0, that the set of solutions, like vectors x1 through x5 in this case, satisfying that system is a vector space, and we're going to find a basis for that vector space. Of course, I'm calling it a subspace here. That's because this is a subspace of R5. We're not talking about all the vectors in R5. We're just talking about the ones that happen to satisfy this system. Yeah, so let me show you how to do it. We basically know most of it. I'm going to just do stuff that we already know how to do using slightly different language, but the different language is not going to come up for a minute, so bear with me. Okay, let's get this matrix in some kind of reasonable form. I've got a 1 up here. I'd like zeros underneath. Let's do that. First row stays the same. This is a 0, 1, -3 plus 4. -1 minus 6, -1 plus 2. Okay, and then 0, and then 5 minus 6, -6 plus 6, okay, 4 minus 9, 1 plus 3, great. Okay, so as I say, I'm happy with this column. Let me move on to the next column. So I look at my next row. I would like the leading term to be a 1, and it already is. So let me get this in reduced echelon form, meaning I'm going to get zeros not just below but also above. And I use the 1 to get my zeros. So I'm going to take this row minus 2 times the row that has this 1 in it. I'm going to take this row plus the row that has the 1 in it. Okay, 1 plus 0. This better be 0, that's the point. Yeah, -2 minus 2. 3 plus 14. -1 minus 6. Second row is not changing. Unless I fail to copy it down correctly, then it might change, but and alright, so what happens in the third row? So 0 plus 0, this is a 0, that's the point. 0 plus 1, -5 plus -7, 7, 0. Okay. I am now happy with, still happy here. I am newly happy here. Let me try to get happy here. So I would like to see that on my third row, I'd like my leading term to be a 1, and it already is. So let's get zeros above it because I'm going for reduced echelon form. So this row needs to change, and I'm going to use the 1 down here to get my 0, plus 4 row 3. And then I'm going to change this to be a 0, so row 2 minus row 3. Okay. 1, 0. This better be a 0, that's the point. Oh boy, 17 minus 28 is negative 11. Negative 7 plus 12 is 5. Oh yeah, this is going to change. 0, 1, this better be a 0, that's the point. Negative 7 plus 12 is 5. 3 minus 7 is negative 4, 0, and then this doesn't change. Okay. Let's find our leading entries. These are the ones that we got. So the leading means the first non-zero as I go from left to right on each row. So first non-zero in this row is this, first non-zero in this row is this, and then this. These 3 columns are our leading columns. Any other columns correspond to free variables. So this is x1, x2, x3, x4, x5. x4 and x5 are free. Yeah. Let me try to be organized about this. I'm going to write them in order, not necessarily going to do them in order. And here's what I mean. x4 and x5 are free, so I'm going to assign those letters that are somewhere thereabout in the alphabet. I start with S and go from there. So we've got 2, so I'm going to go S and T. The rest I'm going to solve for, and this is very easy. This is, I went to the extra expense of actually getting this in reduced echelon form, which means I have less work to do here. x1, so basically this is S and this is T, and I just need to get it to the other side of the equation. So x1 is going to be a positive 11S minus 5T. And x2 is going to be a negative 5S plus 4T. And then x3 is going to be positive 12S minus 7T. Right? So everything I've done so far is stuff that we knew how to do like a week ago or so at least. Let me go back to the actual question. We're finding a basis for the subspace. And so now I'm going to start talking about this new language that we've been using today. We've basically done all the work. We just have to know how to express our answer. My vector is this. And as we've done before, let me separate out the S part and the T part. There's S times 11, negative 5, 12, 1, 0, plus T times negative 5, 4, negative 7, 0, 1. I'm going to justify this answer a little bit more, but my basis is just this vector and this vector. And I'm only really going to justify this because this is our first time doing this. Once you know how this works, you can just literally write this as the answer with no further explanation. So, right, how do I know? I mean, what is a basis supposed to do? It's supposed to be, according to the definition, it's supposed to be linearly independent and spanning. So let's check these two things. Here, I'm going to say a lot of stuff out loud, but I'm not going to write it down. First, let's check that it's spanning. Well, we already determined that any solution to our system can be written in this form. And what does it mean to be spanning? It means that any member of our vector space, which is a solution to this system, can be written as a scalar times my first basis element plus another scalar times my second basis element. And if there was a third basis element, then there would be a third scalar and a third basis element, but we only have two. And that's what we have right here. Any solution x1 through x5 can be written as a scalar, namely s, times this first basis element, plus another scalar, namely t, times the second basis element. So that shows that it is spanning. Let's check that it's linearly independent. What does linearly independent mean? That means that the only way to take a linear combination of these two, in other words, I'm going to point back here again, in other words, take a scalar times my first vector plus another scalar times the second vector. Linearly independent means that the only way for this to be the zero vector is if my two scalars s and t are both zero. But look, here's the easiest way to see it. Go back here, because this is the same thing. The only way for this to be zero, like I would have to have 0, 0, 0, 0, 0. In particular, s would have to be 0 to make this 0, and t would have to be 0 to make that 0. In other words, both of my scalars, s and t, have to be 0. In other words, it's linearly independent. But like I said, this always works. You can just do, you don't have to check that last stuff that I just talked about. You can just find your solution, write your solution in vector form, pull out your S part and your T part, and if there's more, then to do the analogous thing, and then take those vectors, and that's your basis.